Okay, thank you everybody for joining for this tutorial. Together with Abdul Vase, Subarna Chatterjee, we're going to present a tutorial on deep learning and specifically looking into the aspects of systems and responsibility. So our goal is to truly bring up the major opportunities that exist in the field, but at the same time highlight specific problems, both from a systems perspective, design, implementation, scalability, and from an ethics perspective. Okay. And then with all of that, we hope to also highlight several opportunities that exist for data management in particular, but in general for computer science to utilize and extend and improve deep learning technology. And in addition, in the end, we're going to present our view for what we call a new kind of AI, which is actually both new and old, where we think some of these problems, some of the systems and responsibility problems can be treated a little bit better. Okay, so with that, let's start with a quick introduction. So first of all, when we generally refer to AI, the idea is that we start with with data and we end up with predictions. Okay, and in principle, for the context of this presentation, when we refer to AI, we really mean machine learning, and specifically, we're going to be looking into deep learning techniques. Now, technology like that is being utilized these days broadly and increasingly in different areas of our lives, in society and in sciences. And so these are some of the examples that you probably all of you are aware, such as Google or Facebook or other internet-based services utilizing AI technology to create to create their services. Okay, so for example, advertisements is a big user of AI technology. But even other aspects where it might not be obvious to everyone, such as Uber using AI to decide what should be the price for the next ride. So this is something completely dynamic that takes into account the different context, the different user, and so on and so forth at the right time. And even other aspects that traditionally happened with more traditional analytical tools, such as placing products in shelves in grocery stores or in other big stores. And of course, several fintech applications are also extremely interesting. In general, what we're doing with learning technology is that we learn from the data as opposed to manually modeling the world. Okay, and really, when you think about extremely complex problems where the challenges are so big, this is where the potential is. And so, for example, when we have problems where humans, potentially they could have created a manual, mathematical model, but maybe it's extremely hard to do, and so it's more likely to fail in creating that mathematical model. Or for most humans, it would take a ton of time, and so we cannot afford having absolute experts at a time creating models for every particular problem. And so instead, we could have a more automated approach relying on learning techniques. And here's some examples that are more kind of down-to-earth examples to understand. So if we look at just sheer numbers of how many, for example, medical errors are happening every year, and these are human errors, and unavoidable for many different reasons, no matter how much structure we put around the whole process, or how many car accidents that are due to human error. So if it was possible, even for some percentage of those errors to eliminate them, then we would really save human lives. And so this is where the excitement, the true excitement for this technology lies from our perspective. The ability to minimize human error as much as possible in cases where it is extremely critical, and the side effects are they're really affecting human life. Of course, this whole discussion depends on the context and what is really the probability of error. So, for example, when we're discussing about medical errors, it is really different if the discussion is about a state-of-the-art top doctor in a state-of-the-art hospital versus kind of a mediocre doctor in some remote place of the world. And so the opportunity to improve human life is different depending on the context, but still the need is very real. So so it's not as simple as saying that, oh, I would have an expert doctor, because not everybody has access to these expert doctors. Okay, so with that, that is the goal of all of science and technology. And so one thing that we would like to highlight is that, and even though we don't want to go into these details in this tutorial, is that really when we discuss machine learning and AI technology, it's not really the models, it's not really one aspect of the problem, but so many different technologies have to come together to make it possible. Okay, and in fact, just to throw some philosophy here, this has been a goal of follow humanity for thousands of years. And so even if you go back to ancient Greece, you'll find texts where people have been dreaming about ways to improve human life through automation. Okay, so there were even texts where the notion of a robot that serves human beings actually manifestates in those texts. Okay, so with that, what we're going to do in this tutorial, we're going to discuss the opportunities, we're going to discuss systems and responsibility problems, and in the end, discuss a new kind of AI. And again, focusing on deep learning. The tutorial will have 3 parts. The first part will be presented by Vasey, and it will give the systems perspective on deep learning, highlighting specific systems techniques that we can utilize and also open problems. Then we're going to go to the second part, where Suparna is going to present several different aspects that have to do with responsibility and bias. And then for the last part, I am going to take over again and present this new AI method that we call machine knowing, and can help with some of those issues. The tutorial itself is designed in a way that it, for the most part, it is accessible to everybody with some basic data management and data systems knowledge, and it doesn't require any specific AI or deep learning expertise. On the way, we're gonna provide enough background for people to be able to follow. And there's also, for those of you that are interested in going into this material in more detail, there's also a website along with a paper that we're going to highlight, and you can find more information in there. Okay, so with that, we are going to move now with the first part of the tutorial.
In the first part of the tutorial, we're going to look at research that develops techniques to trade off between various metrics, such as accuracy, training time, and memory usage during deep learning training and deployment. Before we do that, however, let's have a refresher on the fundamentals of deep learning. And specifically, we're going to take a systems angle to understand deep learning training and deployment. The central question in machine learning is to map the relationship between one set of objects belonging to the input space to another set of objects belonging to the output space. In computer vision, this relationship is learned between images and their labels, whereas in machine translation, for instance, this relationship is learned between words in 2 different languages. In supervised learning, this relationship is learned from a training data set, which consists of members of both the input domain and the output domain. So in this particular example, we have images as well as their labels. When we're applying deep learning in a supervised fashion, the mapping takes the form of a deep neural network, and the network is trained on the training data set. A neural network takes a data item as an input and produces a probability distribution over the labels. A network may consist of several layers, and every layer has several neurons. Every neuron takes input from every other neuron from the previous layer and produces or contributes one output that goes on to the next layer. Within a neuron, there is a weight associated with every input. The neuron applies the set of weights to the inputs, aggregates the results, and passes the aggregated value through a nonlinear transformation to produce an output. So we can think of a neural network as a bunch of weights, and the training process of a neural network amounts to setting the weights in such a way that the mapping between the input data items and their labels is correctly learned. The training process proceeds in many different steps. The first step is to initialize all the weights in the neural network using small random numbers. Once that's happened, then a forward pass is performed on the network to produce an output. The next step is to quantify how close the output is to the actual label using the loss function. And then we compute the gradient of the loss. Mathematically, this gradient represents the direction in which the loss would increase the fastest. Since we are interested in decreasing the loss, that is, we want the network to closely match the actual labels. What we do is we move in the opposite direction of the gradient. And we adjust all the weights slightly in that opposite direction, and this happens during the backward pass. Here, eta is a hyperparameter, which we call the learning rate, that sort of controls for how eagerly we're going to make these updates during the backward pass. Of course, the training process does not happen for a single data item, but happens for all data items in the training set. And this happens over many different iterations. This process is called gradient descent, that is, we're moving in the opposite direction of the gradient. Over multiple rounds of training, the loss overall gets minimized. And we can stop the training based on a few different criteria. We can stop once the training budget has been exhausted, or once we've met a certain loss criteria. This parameter in terms of when to stop training is controlled by the designer of the deep learning pipeline. And if for some reason the loss does not decrease as expected, there are several ways to debug this process by either using random restarts or properly adjusting the learning rate using some learning rate schedule or some schedule for how the learning rate can be adjusted with the training process. Once a neural network has been trained, performing inference only requires a forward pass on the neural network parameters. In modern deep learning pipelines, because of increasing complexity, we can also use ensembles of neural networks where multiple networks are trained to perform the same task, and the output of the networks is then aggregated to produce the final output. When we look at a neural network from a computational perspective, they consist of several matrix multiplication operations for all of the different layers in the neural network, and these ultimately map to multiply and accumulate operations, and these operations lend themselves quite well to modern GPUs with massive amount of data parallelism. When we look at a neural network from a data movement perspective, on the other hand, what we observe is that the forward pass produces intermediate results for every layer. These intermediate results are stored in the GPU memory as they are required during the backward pass. So they're stored and then reused during the backward pass. The memory footprint of the neural network comes from the training data, the network weights, and the intermediate results. During training, the majority of the footprint comes from the intermediate results because they're produced for every single layer in the network. During inference, because there is no backward path, so these intermediate results do not need to be stored, and therefore the memory footprint consists of only training data and network bits, and is significantly less than that of the training process. We talked about training and deployment of deep neural networks because that is something we're going to focus on for the rest of this section of the tutorial. But these processes of training and deploying neural networks reside within a complex deep learning pipeline that originates from data collection and goes all the way to model deployment as well as design. When we are examining a neural network, we care about its quality, that is the accuracy of the network, as well as the resources required to train it. And these resources manifest themselves in terms of time and memory usage. Existing research to improve deep learning pipelines often trade off between these metrics. First of all, let us look at some research directions that trade off accuracy for some improvement in time and memory usage. Compression is one general approach to achieve this trade-off. In compression, various data items in the neural network training and deployment phase, which include training data, network weights, or intermediate results, are compressed. There are various ways to achieve this compression. One compression technique applied in deep learning pipelines is that of quantization. That is to reduce the precision of weights and intermediate results, making the network faster to train and less expensive in terms of memory usage and storage. Quantization can happen in a variety of different ways. First, there is research proposal to reduce the precision of numbers within the network from their 32 or 64 bits representation to k bits. This makes it both easy to operate on as well as more efficient to store these intermediate results as well as network weights. K can be anywhere from half of the precision of the original number down to 1. In addition to reducing the precision of the numbers, there is also work on converting floating point numbers into integers that are easier to operate on compared to the original floating point numbers. Finally, research from the machine learning and systems community also proposed using hardware knowledge to inform how and what to quantize. Pruning is another way to achieve compression. The general strategy is to remove weights that are less useful, and there are various methods designed to achieve this. Magnitude-based pruning is one of these techniques where weights that have the smallest magnitude, which in this case are highlighted in red, are pruned, and this process can be done after training and is completely independent of the training data set. So it's pretty easy to employ, as we only need to consider the values of the individual weights. Another way to prune that is more effective but requires access to the training data set is to first measure how parameters affect the training loss and then prune the ones that have the least effect. As I said earlier, this produces better result than magnitude-based pruning, but requires access to either a training data set or some validation set. Finally, there are approaches that take into account hardware properties to decide how and what to prune in a neural network. Distillation is another technique to achieve compression. The high-level idea is to train a smaller model to mimic a larger model. The larger model is called the teacher model, and the smaller model is called the student model. Distillation proceeds as follows. Training data is passed through both the teacher and the student network, producing an output for each of the networks. We quantify both the empirical loss and the distillation loss. The distillation loss captures how closely the student network mimics the teacher network. And then gradient descent is applied to the student network to jointly minimize both losses. So during distillation, we're interested in minimizing the loss on the training data set, but also making sure that while doing this, the network mimics the teacher network. Shared training is another way to trade off accuracy for some improvement in training time and memory usage. This is applied in the context of neural network ensembles when we're training a bunch of different models to perform the same task. The high-level idea is to train multiple networks in a shared manner. One approach to achieve shared training is treenets. Given an ensemble of deep neural networks, treenets combines the initial layers together to form a monolithic network with various branches. This monolithic network, which is called a treenets, is then trained in an end-to-end fashion using gradient descent until it converges. Within the shared training approach, another technique is snapshot, which trains a single neural network architecture and forces it to visit different local minima. At every local minima that the network visits, snapshot maintains a copy or a snapshot of the network parameters at that minima, and these different copies are then used together in an ensemble. Recently, we proposed MotherNets, which is another technique to achieve shared training of ensembles of neural networks. And the idea here is, given a target set of networks that you want to train, first capture the structural similarity that exists between different members of this target ensemble, constructing the MotherNets in this particular way. This MotherNets is then trained using the dataset to completion. Once this network has been fully trained, it is used as a way to initialize each of the ensemble networks in a way we can think of it as providing a warm start to the ensemble networks, which are then further trained until they converge. And again, this process provides better training time and requires less memory overall, but comes at the cost of some loss in accuracy. So we've looked at how different approaches trade off accuracy to provide better training time and memory usage. Next, we're going to see how different approaches can trade off between the metrics of training time and memory usage. Recomputation is one way of achieving that. In this approach, the intermediate results produced during the forward pass are not stored at all, which means that the intermediate results do not have any footprint in terms of their GPU memory. During the backward pass, when these intermediate results are required, we perform mini forward passes, recompute the intermediate results, and then use them in the backward pass as needed. And this process continues for every layer in the network. Again, trade-offing some computation so that we don't have to store any of these intermediate results. Existing research within the recomputation space is centered on figuring out which of the intermediate results to store given a certain memory budget. The stored intermediate results can then function as checkpoints, and this recomputation or these mini forward passes only need to happen from these checkpoints instead of redoing everything from the very first layer. The first technique that was introduced in this space allocates these checkpoints in a greedy fashion. So picking those layers that have the highest computation requirement and just storing them. Recently, there has been work from the machine learning and systems community that is called checkmate. And the idea behind that is to formulate the allocation of checkpoints as an optimization problem, and then solve this optimization problem as close as possible to an optimal solution using an integer solver. Finally, the approach we're going to discuss that trade-offs training time for memory usage is that of offloading the results. The idea here is that during the forward pass, the intermediate results that are produced are stored in the CPU memory instead of being stored in the GPU memory. What this means is that the expensive GPU memory, which is more of a limited resource, is free and is free to be utilized for other purposes. Then during the backward pass, this intermediate results, when they're needed, are brought back into the GPU memory and then used as they're required. In summary, in this part of the tutorial, we looked at research to improve deep learning pipelines. Specifically, we organized this research in terms of how it trade-offs between various metrics of interest, including accuracy, training time, as well as memory usage. Awesome. We're going to pause here and see if people have any questions regarding the first part of the tutorial. Cool. If there are no questions, then I think we can move on. We'll also stop after the second part. So if anything comes to mind, you can always ask then as well.
So in the previous section of the tutorial, we have seen how we can reason about the performance trade-offs within deep learning pipelines. Now, as these pipelines are being increasingly adopted in several real-life applications, we observe that they may pose certain societal and ethical implications on human lives. So in this part of the tutorial, we will talk about some of these concerns and how we can mitigate them through an approach of responsible AI. So let us begin by taking a closer look at some of the unfortunate instances where deep learning based systems have led to discriminatory inferences or biased predictions when they were used within certain social systems. So for example, in 2014, Amazon came up with a learning-based hiring tool that automated recruitment within the company. And when this tool was used within production, it was found to be discriminatory against women as it preferred male candidates to female candidates for technical roles. As a second instance, the US healthcare system used an AI model that predicted which patients would likely need extra medical care. And a few years back, this model was also found to assign a lower risk rate for Black people than white people for the same disease. And thirdly, many of us have heard about Compass, which is an AI-based tool to predict the likelihood of recidivism for crime defendants in the United States. With this tool, there are plenty of examples where several Black people have been wrongly sentenced simply based on their Compass score. So the obvious question that arises here is, why might AI models sometimes behave this way? Well, the answer to this would be the fact that these models are far from neutral, because humans, who are the creators of AI, they themselves belong to a world of historical inequities where there is a systematic maintenance of stereotypes and prejudices towards certain social groups. So for us humans, it's too easy to let our subtle, our unconscious biases to infiltrate while designing these deep learning pipelines, which AI, of course, then automates and perpetuates. Now, what's of more concern here is that it is not one, but multiple stages of a deep learning pipeline where underlying human bias can seep in or infiltrate, regardless of the intentions of the technical developer. Again, referring back to the pipeline structure from the first part of the tutorial, we noticed that there are three main stages of data preparation, model design and training, and then inferencing. And each of these stages can be broken down into sub-stages, which, if unchecked or unverified, may reinforce existing social inequalities. So for example, if we look at the first stage, the way we select or sample the training data itself can lead to unfairness. That is, when collecting data, we may unintentionally exclude marginalized groups, or sample from incomplete data, or label data inappropriately such that predictions are unfair for certain demographics. And this is exactly what happened with the Amazon's hiring tool example. So the data they were using to train the model was the past 10 years of resumes, where most applicants were men due to the inherent male dominance in the tech industry. So automatically the model prediction was also gender biased. Then comes the phase of model design and training, where biases can occur as a result of algorithmic limitations. So a common type of model bias is overfitting, that is fitting so specifically to a training data set that it gives poor performance on the test data set. Or we might even pick and rely on very sensitive correlations as the basis of predictions, which again can also amplify societal bias. And this is again what happened with the example of racial discrimination in healthcare, as the designers of the algorithm relied on, or they used previous patients' healthcare spending as a proxy for their medical needs. And this became an incorrect interpretation of historical data, because income and race have been historically highly correlated metrics. So designing the decisions based on such sensitive correlation led to the algorithm to provide inaccurate results. And lastly, unfairness can stem even at the inference step, as we do not really understand how to map the probabilistic scores that we get from our models to concrete actions. So for instance, in the context of COMPAS scores, each defendant gets the score from 1 to 10, with 10 being the highest risk. But then how do we interpret these scores? So what do they actually mean? So will a high COMPAS score necessarily imply say longer sentence if a person is found guilty, or does it mean that we immediately arrest the person purely out of the score, or perhaps it's just a simple number that indicates that we have to stay say vigilant and monitor the activities of the concerned person, right? So we don't really know how to interpret these scores and then map them to well-defined actions. So basically, for all these examples, we can see that it is ultimately the human in the loop aspect during designing deep learning pipelines that leaves too many loose ends to infiltrate and propagate biases. And this eventually leads to a discriminatory outcome based on demographics. So then a concern here is that how severe can this get? So well, again, at this point, we might think that even for a biased AI tool, it's not that all users are victimized. It's just that a certain section of users are affected. But then again, with this thought process, we'll be mistaken, because bias not only hurts those who are discriminated against, but it also hurts everyone else, because it reduces people's overall ability to participate in the economy and society, and then it degrades the quality of human lives. So it would likely affect the whole society in general, and then everyone can become a victim of distorted data and results. So to summarize the problem, as we bring in technological innovations such as artificial intelligence within complex social systems such as criminal justice, or health diagnosis, or hiring, or promotion, if we are not careful enough, our use of AI may reinforce existing inequalities and lead to systematizing the discrimination that we already have in our society. Again, well, there's no denying the fact that we do have a serious concern here with several challenges lying underneath. But there's also a ton of opportunities amidst these difficulties, which, if we take care of, can actually lead to a bright AI augmented future. So moving forward, we will review research across two dimensions that can help overcome some of the issues that we've already discussed. So firstly, there is a growing body of research on how we can incorporate responsible AI practices at every stage of deep learning pipelines, because each stage offers a unique opportunity to reduce underlying sources of unfairness and helps creating a better technology that's more fair and honest. So the first phase is preparing our data. So while no training data will be perfectly unbiased, but there's still an increased possibility of building a better or a more inclusive pipeline if we carefully consider the potential sources of bias in our data and then we take steps to address them. So one of the most important or one of the most effective approaches is to make sure that the training samples include diversity to avoid racial or gender or ethnic or age discrimination. Once the raw data is collected, it's important to proactively look for prejudicial or discriminatory correlations between the features and the labels. So for instance, several works show that during labeling, it is critical to ensure that there are multiple and different human annotations per sample and that these annotators should come from diverse backgrounds. And then once the data set is ready, when we are ready to split data for training and testing, we can follow similar intuitions to create diverse and inclusive test sets. Because again, if we use all our best inclusive data for training, then we could lose out at test time and maybe get an overly rosy picture of our model's performance on underrepresented subgroups. While doing all of these for data preparation, the general approach these works also follow is to document the methods of data collection and cleansing and then allowing others to examine if the model exhibits any form of bias. So the idea here is that this kind of transparency helps to perform the root cause analysis of the sources of unfairness, which can then be eliminated in future iterations. Next, we move on to the phase of model design and evaluation. So when building and evaluating deep learning models, many organizations, for instance, Google or Microsoft, follow a human-centered design approach. So this approach requires thinking deeply about our particular use case and what impact the model can have on end users when things go wrong. So this means understanding the impact of different types of errors for different user groups. So this is where it's important to think about potential fairness issues. So for example, it's critical to ask questions to understand if model errors affect all users equally or if they're harmful to a certain user groups. So once we've thought this issue through, we'll be better able to decide what performance metrics it makes sense to optimize for, and then we can evaluate the trade-offs between them. And again, even at this stage, it is crucial to engage with experts from the fields of ethics and social studies to understand and account for various perspectives. So it's important to conduct rigorous unit tests with inputs coming from diverse background of testers, and this can help identify which group of people might be most affected by the model. Finally, once the model is ready to be deployed and also during post-deployment, it is crucial to continue monitoring and updating our models through regular user feedback. So we should regularly audit the production models for accuracy and fairness, and then regularly retrain and refresh these models with the newly available data. So now that we have discussed some of the responsible AI practices, we also understand that these are more of guidelines or roadmap that make AI more beneficial to society by avoiding the creation and reinforcement of existing biases. But ultimately, there is no way to completely eliminate AI bias. And therefore, it all comes down to how we do the trade-off between the benefits and the harms, and how we think about the net effective gains of using AI in our society. So herein, we arrive at the second step of understanding and reasoning about the tension between the functional success of deep learning pipelines and the ethical and social implications of it. A good understanding and reasoning about this trade-off can actually help us weigh the net benefits of using AI and accordingly decide on how much of autonomy we would like these systems to have for any application. So for instance, if we take the example of using deep learning pipelines within courts and judiciary services. So then on one hand, we see biased decision making for certain demographics, and we also see misinterpretation of the model outcomes. But then on the other hand, we also see how AI has helped to speed up backlogged courts or enabled easy access of databases to judges from previous legal cases, and even saved the legal fees due to reduced usage of manpower. And this is also true for other applications. So on one side, AI has the potential to speed up the process of hiring and screening through resumes, or even advance the state of art in healthcare. But it can also amplify the underlying demographic discriminations that we have in our society for each of these applications. Therefore, to be able to decide the extent of using AI, it is crucial to identify and reason about this benefit versus harm trade-off. So toward this, there are two ongoing directions of work. So firstly, there are several efforts to design cost-benefit analysis or CBA frameworks that are primarily used in the domain of business and economics. So in a CBA framework, all the costs and benefits of a given situation are converted to units on the same scale. That could be monetary or some other utility scale like well-being. And then a decision is made based on whether the benefits outweigh the costs. Now, while CBAs of course support systematic thinking of the consequences of different actions, and they open rooms to measure the societal impact of these pipelines, but at the same time, there exists a separate school of thought primarily originating from researchers of ethical science background who highlight basically the limitations of this approach when it comes to measuring the ethical impact of systems that are related to environment or safety or health. So these studies show that CBA alone cannot be seen as the answer, because it is technocratic and can hide controversial value judgments. And further, CBA does not recognize the fact that human values can also be vague and unquantifiable, right? On top of that, social science experts also highlight that the very act of economic valuation of a human morale can change people's attitude to it, which also kind of explains why applying CBA to complex social systems have always attracted so much of controversy. So the second approach toward reasoning about this trade-off relies on public participation and collecting opinions. So this approach states that the legitimacy of any emerging solution can be achieved through consultation and inclusive public deliberation. To implement such deliberations, a small group of citizens can be guided through controversies by experts and moderators from diverse domains, which brings forth the societal expectations of the common people belonging to diverse demographics. But again, both approaches point to the need to be able to find means to navigate this benefit versus harm trade-off, so that we can make educated decisions about if AI is needed for a specific situation, and even if that's the case, to what extent we should use it. If we know how to carefully prevent the unnecessary use of AI and then use it responsibly, then this can really go a long way to also keep our planet greener and healthier. In a 2019 study, Emma Strubel estimated that training a single deep learning model can generate up to 626,000 pounds of carbon dioxide emissions, which is roughly equal to the total lifetime carbon footprint of 5 cars. Therefore, we can imagine that if we are able to carefully control or reduce the use of AI, then even the slightest reduction can lead to significant climate benefits by lowering the carbon footprint. Also, not to forget that classically there always has been examples of using several non-learning based computing techniques that have the ability to tackle the decision space of complex problems. In fact, there is a growing body of work which brings back those classical approaches of problem solving to modern application contexts. So for instance, in 2018, the data calculator took inspiration from the periodic table of elements to reason about the performance of the astronomically large design space of data structures. So analogous to the fundamental elements of the periodic table, this work uncovered the first principles of data layouts to compose numerous data structure designs which are used within modern data systems. The next part of the tutorial will cover more about such computing approaches and the design principles of the data calculator. So as we near toward the end of this part of the tutorial, we'd like to conclude by drawing attention to some of the brighter sides of this topic. So at present, there are several radical and activist groups that have been formed with minds from diverse backgrounds. And this not just includes technology, but it also includes ethical sciences, legal studies, sociology, and philosophy. So for instance, Black in AI is a group for sharing ideas and discussing initiatives to increase the inclusion of Black people in the field of AI. Embedded Ethics is an initiative at Harvard for embedding philosophers directly into computer science to teach students about the social and ethical implications of their work. And these groups encourage and foster cross-domain interactions and bring in interdisciplinary insights, which are being further adopted by tech companies to design and build frameworks and tools that facilitate a responsible usage of AI. So for instance, FairLearn is an open source community driven project led by Microsoft that helps data scientists improve fairness of AI systems. So it is basically a Python toolkit that assesses which groups are negatively impacted by a given model, and then it allows comparing multiple models in terms of fairness and accuracy metrics. ML Fairness Gym is an endeavor at Google that allows data scientists to run simple simulations to explore the potential longer-term impacts of deploying machine learning-based systems in social environments. In the end, it is really important that we continue making ourselves aware and we create a diverse culture of support so that together we can build an inclusive ecosystem that is respectful and accepting to the differences across the world, and at the same time promotes and encourages equality of access to technology and opportunities.
Cool. We'll pause here again to see if anyone has questions about this part of the tutorial. Okay, so if no one has questions now, then maybe we can move to the next part of the tutorial, but feel free to write to us on chat also if you have any questions that comes up later.
Okay, so it's time now to move to the third part. So from the first two parts, we learned some of the basics of how algorithms and optimizations manifestate from a systems perspective in deep learning. And from the second part, from Suparna, we heard how certain aspects on how the whole process is happening can lead into ethical problems, particularly because humans are in the loop making decisions. So now in the third part, we're going to build on top of that and also think through a new approach for doing AI that can help some of these problems. Okay, So just recapping a little bit the whole aspect about how much we can trust Turing processes. And so, a very interesting thought process is, given what we heard so far, especially from the second part, but also from the first part, understanding that the whole process is rather stochastic, a very interesting question for all of us is, would we trust, let's say, a bridge being built by AI, or an airplane being designed and built by AI, or a building, in the same way that we trust those structures today being built by engineers based on mathematical models? And so that's a very interesting question. And if you think about the stochasticity of the whole thing, and the chance for errors, you cannot really trust a bridge that fails, 1 out of 100 times without understanding why. So overall, this is going to create growing uncertainty and mistrust for AI. But at the same time, as we discussed in the beginning, there are really so many very real opportunities. And so our goal is to, as much as possible, utilize these opportunities while being mindful of the problems. And so one approach that Subarna brought in the discussion with the related work that she presented is that there's a whole movement in trying to involve humans in the loop, not only in terms of making decisions, but in terms of safeguarding the result, safeguarding the final result of an ML pipeline. So that can really help when we are actually utilizing AI to make sure that there's a set of people that truly understand how this AI was created and how it should be used. Of course, all of this is quite manual again, and so it doesn't really scale. And so the question is there a better way? So what does this mean, a better way? Ideally, what this would mean is that there's a process that is not so stochastic, and there are fewer opportunities to introduce bias and errors from humans. Okay, and so with that, we now move to the very last part, where we're going to try to build on top of this notion and see what we can do with that. And we're going to do again a bit of a trip in philosophy and go a few thousand years back and kind of where the beginning of science was, more or less. And so there was a time where people, they were thinking that they would explain the world with kind of arbitrary ways. And then Thales was the first one to say, well, we should actually be able to reason with concrete logic about things, okay, about the human life and the physical world. And then there was a series of philosophers that kept building up around that idea for years and years, all the way to Plato, that in the end kind of characterized that whole reasoning process as an effort to start from a fundamental set of first principles that they called elements, out of which the whole physical world was constructed. And so the idea was that if we knew those 4 physical elements and we knew how they interact, something, reasoning would actually be enhanced. And so again, actually now, many hundreds of years later, in the 1600s, this is when that idea became slightly more concrete, still vague, but slightly more concrete. And so Leibniz was the first to say that, well, there are so many first principles out there in the world. If we knew all of them, if we knew how they interact, what are the rules that govern their relationships, then we could know what happens every time we synthesize a solution out of these first principles. Not a solution, we synthesize a construction out of these solutions, out of these elements. And so then the idea was that, and the vision was that well, if we then know for real these first principles and all of them, then we would actually explain everything in the physical world. And also, Leibniz had this very interesting quote, which was, let us calculate, which meant that if indeed such an engine existed that had the first principles and the rules, then people would never have to fight again, because whenever there was a conflict, they would just ask the engine the question, and the engine would just tell you the true answer. Okay, so in more practical terms, because this is kind of an arbitrary, kind of a bit of a vague vision, in more practical terms, this has happened in several, let's say, subfields of science. So we all know the periodic table of elements, and in principle, it is very much of the same nature. So what we have here is that we have a set of first principles. In this case, they are, the atomic number, the electron configuration, and so on and so forth. And then those are properties that if you bring together, they actually create the chemical elements. And so Dmitry Mendeleev, and actually several people before him, they were really trying to find out which are these first principles, how they connect, how these elements can be characterized, the chemical elements can be characterized. And simply, Dmitry Mendeleev was the last person to work on this vision, because his periodic table of elements was the one that kind of we all remember, but he was not the first one to work on this. There was a series of people that were trying to work in this vision, and they were all building on top of each other. And so the thing is that when this was eventually stabilized and presented, it's not that it only gave us some kind of understanding about the these chemical elements, but at the same time, it also created a structure that we could use for innovation. Why? Because that periodic table of elements was full of gaps. So there was specific sets of combinations of first principles that there was simply no known chemical element to represent them. But since it was part of the structure, scientists started wondering if those elements would actually exist in the world, and we just simply not know about them yet. And so for 100 years after the periodic table of elements was created, scientists kept doing research to find out if certain elements in the cells that were empty existed. And this is one of the last ones that was discovered a couple of years ago in Japan. Okay, so this is what we started working on about 7 or so years ago at our lab at Harvard, wondering if it is possible to create such an engine that it would understand the first principles, understand the connections, and we could use that instead of learning. And then the idea is that if we were to do that at least for one complex problem, then we can show that it's possible, and then lots of future work can happen here. So of course we started thinking about data systems, because this is the complex thing that we are building in our field and in our expertise. So the interesting thing with complex systems today is that they're truly everywhere, and so any kind of even small innovation there, it can really have impact. And of course, the other thing today is that it's not being used only for traditional analytics, but data systems are prevalent and the core component also in the huge trend that is happening right now around AI itself. And so anything from data preparation, feature generation and storage, all the way to how models actually are being executed and scale, it is being governed by data systems. So one of the very interesting issues with data systems is that because exactly of all of this explosion in applications and in usage, and the diversity of these applications, there are continuously new requirements, both in terms of what we do with those systems, what kind of workloads they have to work with, and also the context, the actual hardware where they're supposed to be deployed. And those contexts, that context actually changes all the time. And the need for new kinds of data systems that is tailored to those contexts is growing. And of course, a very relevant aspect here of part of the problem is that at the end of the day, all of those things, they sum up to cloud costs, because if you have a system that is not optimized for the workload or for the hardware, cloud costs rise, and with big data, cloud costs really rise to the point where it becomes even prohibitive to apply systems to specific scenarios. And so, because of everything being data-driven right now, data systems are the major bottleneck. And so there is a continuous tension in terms of building new data systems or utilizing existing data systems by adapting them a little bit. Of course, ideally, what we would do is we would create the perfect data system for the workload, for the hardware, for the exact application that we have at hand. But of course, we're not doing that. And the reason that we're not doing that is the complexity of building data systems. And so this is a manifestation of a very complex problem that human beings are, we don't really have so many experts in data system architecture, so we can actually go ahead and create, arbitrary numbers of data systems, every week. And so what we're doing is that we're simply adapting existing data systems to the context in the best possible way. So if we look at the process of building data systems, it's really, if we wanted to build something tailored from scratch, we would really have to have some kind of a small team of true experts with tons of years of experience, and then give them several years at a time to design this perfect tailored system. And so this is extremely expensive, both in terms of time and in terms of money, and so it simply doesn't scale. So this fits exactly that paradigm of that we're discussing in the introduction of the tutorial, of a very complex problem that we don't really have enough human experts to keep solving this problem again and again. And at the same time, even for the experts, it takes several years at a time to create these solutions. And so it's exactly a situation where if you had some kind of an automated approach, an AI approach, that would make perfect sense and really help. Okay, so if we look internally into data systems, as you all know, what we find is fundamentally, we find data structures and data-driven algorithms. But things become truly very complicated when we think through how these data structures and these algorithms, they interact with each other. And so this is where fundamentally the complexity of data systems lies, because of everything that we want to do and the fact that most of what happens involves multiple different data structures, multiple different algorithms, and exactly what we're using and when, in what order, it really makes a huge difference in performance and resources utilization. And so what we started thinking through is, can we think about this massive problem in a way that is about first principles? So can we find a small set of fundamental design principles and rules that govern the relationships, out of which we can actually synthesize, ideally all possible systems, but because the world is such a heavy world, a massive number of data systems, way beyond what we can find out there in industry or in literature today. So what does this mean? We're gonna, since it's not possible to have a more in-depth discussion about this, it will take a lot of time. We're gonna do an analogy that hopefully kind of helps people understand the primary concept here, and then people can we'll give you links so people can follow up and see more detailed materials. So what we have here is a sequence of words that they look mostly random, right? And so you can see a set of words that you understand. We all use those words, maybe even every day. And so for the most part, they look like a random set of words. So if I take here some subset of these words and we put them together in a very particular order, then we get this very interesting quote here that if you're seeing this for the first time, it feels like, oh, this is something potentially new, but even if it's not new, it's quite brilliant to think through that. And again, this happened by the interesting thing here is that this happened by us taking a subset of this world that we all knew about, but then putting them together in a particular order creates something extremely powerful that maybe we couldn't see before. So what happened here? We started from an alphabet, okay? We started from the English alphabet here. Out of the alphabet, we created multiple different words. And then using grammar, we created sentences that are meaningful. Okay? And then of course here comes the human intuition and critical thinking to say that, oh, this is grammatically correct, but it's also interesting and powerful and so on and so forth, right? So there's this fourth level of judgment that comes from us as humans. And this is the same thing that we've done for data systems. We started by thinking, what are the first principles, the elements that characterize data systems? Out of this, we can actually create arbitrary data structures and algorithms, data-driven algorithms, as independent components. And then by being able to understand the rules, so kind of the grammar of what governs the relationships between those data structures and algorithms, what happens if we put multiple of them together to achieve a specific operation, for example, and what's the best way to do that, and so on and so forth. And that creates what we call a grammar for data systems. Now we can actually create arbitrary data systems. And given the workload and the hardware context, and given a particular data system design, then what we can do is that we can actually evaluate what would be the performance of a data system, given the workload, given the hardware, and on top of that, build search algorithms that can navigate the space. And again, we cannot go into the exact technical details here. People that are interested can take a look at the data calculator paper from Sigmod 18. There is also a tutorial in Sigmod 19 together with Tim Kraska, where we blend this kind of design approach with the learned approach. And there's also, if you look at this year at Sigmod student competition, there's a paper that discusses the how we build the search algorithms using learning on top of that construction. Okay, so just to give you an idea of what are these first principles, so specifically for data structures, one of these core components of data systems, what we started doing is that we started thinking in detail through these data structures and through these data concepts that we need. And so, for example, a design principle can be how we order data in a particular node of a data structure, whether there's a pointer from this node to another node to connect them, or whether you put these two nodes together, sequential in memory or in disk, which creates certain properties. And then we also started doing clustering of these design concepts. So, for example, you see here partitioning, logarithmic design, fractional cascading, and so on and so forth. And we started clustering them with respect to whether these design principles appear in particular data structures, in particular classes of data structures. And we created this visual, effectively, representation of the design principles and how they manifestate in the known space of data structures. And this is what we call our version of the periodic table of data structures. And so the way you can think of this is that is like a visual summary of the actual design space that we have created in a more formal way. But what is interesting about this is that even visually now, you can see that most of the space is actually empty. So every cell here, if you see the word done, it means that we know of at least one research paper or one system that applies this class of design principles to this class of data structures. But for the most part, it is actually empty. Of course, everything about B-trees is kind of done, but for the most part, the rest of it is quite empty, which means that even after 50 years of studying data structures, there's so many opportunities to innovate and find designs that are great. Of course, it doesn't mean an empty cell doesn't mean that someone hasn't actually studied that part, that combination of design principles and maybe they found a negative result for a particular context and they haven't published it, which is a side effect of the way that we publish. But really the number of combinations is so huge that this implies that there's a huge number of great designs in there. And people are still publishing about 100 new data structures per year. And so this can help us accelerate those findings. So by doing a bit of counting, we realized that we can actually create more than 10 to the 100 possible. In this case, we refer to specifically to key-value storage engines. While if we look at the numbers of just pure data structures that people have published since the beginning of computer science, it's actually not more than 5,000. So the difference is so huge that it's indicative of the potential if we were able to actually navigate that space automatically or even semi-automatically and find good designs. Just for fun, here's a comparison with how many stars we estimate that we have on the sky, and so that gives you an idea of how many possible data systems exist. In our own research, one of the latest things that we're doing is that we're creating a key-value storage engine using these ideas that I described here, and we find that we can actually create, for mixed workloads, we can actually create key-value storage engines that are 100 times faster than WiredTiger and RocksDB and DynamoDB in mixed workloads, meaning that we have both reads and writes at the same time. And the cool thing here is that we can do that by designing and generating the system in a matter of seconds, as opposed to spending years with expert designers iterating through designs and so on and so forth. For more of that, you can we will link on the website some of the latest research that we have in the space. Okay, so with that, what all of this means? It means that the vision that Leibniz had as a kind of continuation of the great philosophers from the past, it might be possible. It might be possible to create this generic engine that reasons about the world, and of course, the trick is to create that for very specific problems and have concrete results. And so we have been working on the data structure space, on the key value store space, and also for the last few years, we've been investing in doing the same thing for neural network design. And we have an ICLR paper that you can take a look at in 2021, and also in image storage, which are again two very complex problems where if we wanted to have human beings figure out the design themselves, it's something that is not necessarily a scalable way to do things. Okay, and to start closing a little bit and summarizing what we discussed, there's a ton of opportunity for deep learning and ML in general to help with very complex problems in society and in science. But it is extremely crucial to have ways to truly govern how we use and how we build and how we use this technology. And this is because, again, it is the way the whole flow of development is. Human beings are involved throughout this process, making critical decisions. And so human beings, we all bring with us our biases. So that has to be carefully done and protected. When we use AI, so one thing is how we build AI. When we use AI, we truly have to understand how a result, a prediction, how it has been created, and the fact that it's not really written in stone. And so any result that we get out of AI, it is a probabilistic result. And it is a result that it's truly based and created out of the data, and it is as good as the data that it was used to create that result. So it's not necessarily a prediction that comes out of AI. It's not necessarily true. It simply reflects the data that it was given. I think we all collectively as a community, we think that research in the space is only going to explode in the next several years, exactly because of the kind of opportunity that exists here. Now, within our own space in database research, we think that there's a ton of opportunity, exactly because everything is data-driven, but specifically when it comes to how we scale processes, how we model data, thinking and creating abstractions about the complex workflow, and definitely thinking about end-to-end solutions. These are unique opportunities for the data management community, because this is exactly what the data management community brought to the analytics problem with SQL and database systems. With that, we're going to thank you for attending our tutorial. Online on our website, you can find more information about all this material. You can find links to all the related work, and you also can find this video. And we're very open to remarks, comments, and feedback. And so please stay in touch if you would like to discuss anything else with us. Thank you so much. Okay, thank you everybody for staying online and watching through our tutorial. We're here, all of us, myself, Subarna and Vase, would be very happy to answer any questions now for the next 10 or so minutes. And we also have an office hour slot tomorrow morning ET time at 9 a.m. And you're most welcome there as well. The website that we mentioned as part of the tutorial, you'll be able to find the link there in our labs website over the next couple of days. And this is something where you'll find the video again, and but also you'll find perhaps the most useful thing will be a very nice way to navigate all the related work. So every citation you'll see on the paper, you'll be able to find it kind of clustered and with links and so on and so forth. I do not see any questions on the chat or raised hands. I think if people are gonna also from the attendee list, if you would like to speak, you could raise your hands and you could be promoted to a panelist and speak live if you want.
So let me ask a question. Okay, so this is Jag. This is Jag. So, you have you presented this compelling vision of, I'm going to call this kind of the Leibniz dream, right? Yep. And as a practical matter, we probably won't quite get there. And getting to some, I guess what you're saying is that it's worth the effort, because even if we get halfway there, that's going to buy us a lot. Yep. And I wanted to probe that a little bit and say, does which half matter? What would be intermediate milestones that you could identify, perhaps, or I guess there are too many dots for me to connect from. You have a matrix of data structures and the kinds of analyses and parallelization and so on to the Leibniz machine.
Yeah, so I mean, obviously this is very complex to think through, but So let me back up and say that the way we kind of organically we started understanding this whole process is that you need the first principles of some, whatever is the problem, you need the first principles, and the first principle is the smallest possible decision every time, design decision. Then you need the rules that say that if you put those 2 or 3 design decisions together, this is a construction that you get. And then you need models to assign some kind of cost. So in this case, where we're designing data structures or data systems, the cost is latency, throughput, and so on and so forth. But you do need those models because then you're going to go back and start being able to compare arbitrary constructions that you're creating. Because once you can do that, you can take 2 designs, 2 constructions, and you can compare them. And once you can do that, now you can also create search algorithms, even if it is, in the beginning, a brute force search algorithm. So you need, it seems that you need all those steps. And this is what we have done the last few years. We've done it first for data structures, for key value data structures, and then for key value storage engines. And we're actually quite excited about the second part because it has this second level of complexity where you don't only worry about the design of and the performance of a single data structure, but you worry about all these other peripheral issues that have to do with concurrency and interaction among different data structures in memory or on disk. So it's one more level of complexity, but essentially it boils down to being able to create again a grammar of rules and a new set of cost models. And once you can do that, then the rest is the same process. So what I'm trying to say with this is that we seem to have a set of components that if we're gonna keep doing that for different problems, we should have similar components. So a way to have principles, a way to connect them, a way to judge them, and a way to search using all the other layers. So one thought process is that if we keep doing that for 1 problem at a time, and then 2 problems, and then 3 problems, and then 4 problems, and what I'm going to say next is wishful thinking. Maybe eventually what happens is that we observe patterns about effectively problems that are similar across these different applications. And so potentially we can start extracting components of these different machines that we created for data structures, for systems, for image storage, for neural networks, or any other problem, and extract the similar components that we have in these engines and potentially reuse them when we make the next one. So that part is more wishful thinking about, but it is the notion that if we keep solving problems using a similar overall approach, we might find common patterns in our solutions that allow us to create a more generic engine that when we go to solve a problem next time, it's a little bit easier. And so that's why I think about this long term without, of course, having any proof that this is possible. Our next effort is to do that with image storage and neural networks. Image storage, it's a little bit of cheating because effectively we are using some of our existing work. It's not an entirely new problem. Neural networks, on the other side, it is a different problem. We're not really reusing anything from before, and there are aspects that are different. For example, we cannot create analytical models like we can do for systems for when data is on disk at least. And here we have to have more empirical rules, and out of that create the costing. But effectively, we have to create costing. So there is a similar pattern there.
Thank you.
Yeah.
Thank you very much. This is great. Very, very inspiring tutorial. Appreciate it.
Thank you, Jack. Okay, so if people don't have any more questions, let me repeat, we have our office hours tomorrow at 9 a.m. ET. I would highly advise people to take the chance to talk to Subarna and Vasey. They really, really know this area very, very deeply. And so I think it would be a fun discussion for everybody that might care about neural networks and ethics also in particular. Vasey, Subarna, would you like to close this. Is there any kind of last segments you want to make before we close?
No, not really. Sounds good.
Yeah,
Yeah,
same here. I would just like to add like I mean you've already covered that, but I was thinking that when we design the costing of data structures, one interesting aspect here is that we also don't have to get to the point where we estimate with extremely high accuracy the performance of every data structure. I mean, we can get to the point where what we've done is we've gotten to the point where we can rank the data structures, and that kind of accuracy helps to go forward. So I would just like to add that thing here.
Yeah,
But
that makes life more easy. It does depend also. So the choice of metrics is an issue. So sometimes ranking is important, so we can choose the best design. Other times we want to bring, for example, say if you were to run this on the cloud, it would cost this much money, and then getting the more exact the model is, it starts becoming a bit more important. But yeah, there's a lot of flexibility in many cases. Okay, thanks everybody. Really, thank you so much for staying and listening to our video. We really appreciate it, and we'll be very happy to meet you during office hours or in any other occasion and answer your questions, or just see you in person and just talk. Thank you so much. Bye-bye.